Thank you very much. So it's really my pleasure to be here to be giving this talk today. I would first like to begin by acknowledging the traditional owners of the land on which we meet today. And I'd also like to pay my respects to elders past and present. So today I'm going to talk a little bit about genetic improvement. I have to admit that I've only been working in genetic improvement the last few years.
Sorry, Myra, you're again a bit faint.
Okay, is this better? If I just hold it to my, is this better?
That's much better.
Okay, I'll just hold the mic then. So I've only been actually working in genetic improvement for the last few years, although I've been working in software testing for many years. And I started a little foray into automatic program repair, which of course is obviously a subset of this. But I really wanted to talk today a little bit about some of the things I'm learning and leave you with some food for thought. So this is really made to think a little more about some of the things that are happening in genetic improvement. So just in case anybody in this room is not that familiar with, I doubt you are, but not familiar with genetic improvement, essentially we have a program, and I'm looking at sort of the traditional view of genetic improvement, which means our program is functionally correct. So we have it, it works. However, and we have some test cases or specification which tells us that the program is correct. However, there's some problem with the program that we want to fix or improve. So perhaps the program maybe is too slow, or perhaps the code base is too large, or we have security violations in the program that maybe don't appear as faults. We might also be using too much energy. So these are all the kinds of things people have been using genetic improvement for. And what we can do is we can say, well, we have these properties, and often they're non-functional and they're not being satisfied. So what we want to do is we want to be able to fix those somehow. We want to fix them automatically. And so our favorite way to do this is we use genetic programming. There are other ways we can probably do this. We use genetic programming, and in the process, we make small changes to the program, and we use our test suite or our specifications to make sure the program retains its functionality, so it's still correct. But then we add something else to the fitness. And what we add is going to be based on that property that we're interested in. So if we're interested in energy efficiency, we'll also be looking at energy efficiency. And we try to get them to both converge to be better. So we want to have a correct program that has strong of whatever this other piece is. And now we have our new program and we've improved it. Now, automated program repair is often seen as a subset of genetic improvement. In some ways, by the end of this, I think we're going to agree that maybe there's really no difference between automated program repair and genetic improvement. Although usually we tend to think of genetic improvement as sort of the superset, and then we think about program repair as being only interested in those functional properties or the behavior of the program. Whereas GI, we tend to think about these non-functional properties, which are the things like energy or size of the code base. So there are a couple implications here. So what that sort of indicates when you think about the way that this is being used in the community is that you think about genetic improvement doesn't really impact functional correctness, because we have this separate test suite. We're going to keep our program correct, and we're only going to think about those functional properties. And so these are sort of the assumptions, at least that I went into when I moved into genetic improvement, and I think many of you think about in that environment. So I'm going to start with just give you a little bit of a teaser. So this is actually, there's this notion of pausable patches, right? This idea that when we're building in automated program repair, we want our patches to actually maintain functionality. So I can trivially remove all the code from the program, my test cases will pass and I have a correct program. So we always want to make sure that our programs are still correct. This is a simple triangle program. Actually, I took this from the Piggy genetic improvement framework. And this is the very simple example that they use to show how genetic improvement works. So this is a Java program, and there is a, in here you can see there's a delay. Oops, sorry. Yeah, I'm just trying to get it back. Where's the, is this the, I'm just trying to get the,
I'll just double check.
where's the,
I think the pointer is there. Just,
Okay.
oops, I'm sorry, I accidentally blind someone.
sorry.
Yeah,
we're
that's just the red part.
Okay. Oops. Okay.
Or this one.
Does that work? Okay. So, so here we have this, we have this delay, and what we're trying to do is we're trying to remove that. So the program is just a regular triangle program. However, when it runs, it actually is delayed for some number of seconds. And so this is going to slow the program down. Now, obviously, this is a trivial program, but the idea is to demonstrate to people how genetic improvement works. So if we run the program, the expected and correct output we should see is that we'll just comment out that delay. And in this case, we've now improved the program. We haven't changed any functionality. I'll come back to this one later because I'm not sure we haven't, but at this point, we haven't really changed the functionality. But I've played with Piggy a lot. I like to give it to all my undergrads to learn how to do genetic improvement. And I even show it in other classes, and I've seen lots of different repairs. So here's an alternative. So there is a function inside of that code below the triangle, which is the actual delay function, because it's calling a delay, and what it's doing is it's creating a sleep, and that's what's slowing the program down. So sometimes genetic improvement is pretty smart, and what it does is it leaves the delay in the triangle part of the program, but instead what it does is it just comments out or zeroes out everything inside of that delay function. Now, again, we can say, is this correct or not? Well, it depends what our test cases say. So if we have test cases, and probably the reason we get this is because in the test cases we have, they're really geared towards the triangle program. We care about the correctness of that. So if that's what we really care about, and we only care about the correctness of the triangle program, theoretically, this is now still a correct program because all we've done is taken away the delay functionality. But it's part of this program. If we were to combine this with some other module, people may use that delay. We may decide we really want to use it somewhere else in this program, and now we've actually just removed functionality. So I'll just let you think about that for a while. But they're both correct repairs according to the genetic improvement framework. So there's been a lot of work on this idea of overfitting. And overfitting really means that correctness is going to depend on our test cases. And our test cases in these environments are going to provide our specification. And so we're always concerned if we have test cases that aren't complete, we may have partial functionality. We may actually overfit our solution so that we can actually work in some environments and not others. So this has been a very big issue in the whole automated program repair GI community. And so I want to just bring that up. And so there's interesting work, though, that kind of leverages overfitting. So this is a paper that, it's an older paper from Justina et al. And they were looking at using, I like this paper because it specializes a SAT solver, and it specializes it for a particular class of problems, which is something called combinatorial interaction testing, which I happen to work in that area. So I kind of like this work. And what they do is they take a SAT solver and they specialize SAT solvers to be more efficient for one particular purpose. In this case, for this combinatorial interaction testing. And in the process, what they did is they removed, often the GI removed blocks of code that weren't needed for the problem solving, and they made these SAT solvers more efficient and faster. But as a caution, they're using the word specialize. So in a sense, what they're actually doing is they're overfitting deliberately to kind of create a program that works for one particular problem. So if they try to use the SAT solver on another problem, we have no guarantees that it works. And that's okay in this particular case. And actually, this is kind of a nice way to use genetic improvement. But again, we have only the correctness based on those tests that we're using in this case. So putting that into the back of your mind, what I'm going to do now is I'm going to walk you through a few things that I've been working on that have been making me think more and more about this interplay between correctness, overfitting, what we mean by a correct program, and genetic improvement. So I'm going to start with a very simple example that I call partial specifications. And then I'll talk about two projects that look at a security property that we were trying to use for genetic improvement. And then I'm just going to reflect on all of this and leave you with some food for thought. And hopefully you can answer some of my questions, because I'm looking to the experts in this room to help me. So there's been a lot of work on test suite quality and automated program repair. And people have spent a lot of time looking at this. I won't go into all the details of all the papers. But there's been a couple of things people have done. So people have, one of the issues with program repair is that when you run all the test suites, it takes a long time. So people have done things like reduce, just use samples of test suites in different iterations. They've also used things like lexicase selection, which is considers one test case at a time. They've done things to then perhaps instead just reduce at the end of a program. They may want to just use some test cases and at the end just reduce the excess code that's created from the repair, or people have looked at manual versus automated test suites. And I think this is something we have to look at more. So I'll come back to this, but I think this is really going to be an important issue. And so people have looked at different things related to whether we use specifications and I generate manual tests based on the specifications, or we use some sort of automated tool. And so this led to something we call partial specifications. So this is work I did with an undergrad. She actually presented this at GI a couple of years ago. It's just a very short paper, so we don't have full results, but I think it gets to some of what I really want to talk about. So what happened was she was trying to ask a question. She was working with, actually with the genetic improvement tool. She was working with Piggy, and she started to notice that some of her repairs were very complex and some were not. So when I say complex, perhaps it removed 3 or 4 lines, it added lines later on. And then other repairs seem to provide a much more direct repair, something that a human would be much more likely to make. And she noticed while she was doing this, because I actually asked her to look at the test case problem, not to look at the complexity, but that's what she noticed while she was doing this, was that when she removed some sets of test cases, she sometimes seemed to get simpler repairs. And so this intrigued her. And this is why we looked at this problem. So what we did is we took, so this is, here, this is the triangle program. And you can see that these are just tests. And this one set here are for equilateral tests. And these are for scaling. And this is kind of important because these are semantic sets of tests. So these test a certain part of the program, and they're not just random tests that were generated. So for instance, if she just removed like all of the equilateral, or she just removed all the scaling, she may get a different result. So what she did is she removed sets of test cases based on that class of specification and ran the repair, and then would get a pool. So rather than just run it once, because we know we're overfitting now, right? We know we're not going to necessarily get a correct program. So she would run a number of them in parallel. And then at the end, she would test them all against the full test suite, and then just select the simplest repair from that group. And what we found was that, so this is the middle one, as we call a simple repair. So this is the triangle program, and you can see on the left here, the bug is in the second if A is greater than C, there's a B equals temp. It should have been C equals temp. And the repair actually gives us the correct repair there. So it's a very simple repair. However, the one on the right is a little bit more complicated. So it adds and removes a bunch of code, still ends up being correct against the full test suite, but this is what we would call more of a complex repair. And if we look at this further, if we look at the top, that column shows 4 rows: success, simple, and then there's some averages. So success means that over 15 runs, we were able to successfully find a repair. Simple means how many of those were in that simple category. And you can see when we ran all test cases, 0. However, when we ran them with removing all the scaling or removing all the scaling equilateral, we started to get numbers like 8 or 7 simple repairs. So what we found is that by removing some of the test cases, we were able to get these better repairs. But of course, along the way, many of them didn't work because we had overfitted and we had kind of removed some of the functionality. So I think that's interesting to think about, because it makes sense to me. The search is working. The search is providing a little more degrees of freedom. If you think about how something like a triangle program works, and if we have test cases that are semantically tied to the program, and there are certain parts of the program, well, the least likely part of the program we're going to use is equilateral. So perhaps if we remove those tests, we give it more freedom to make interesting changes. Okay. So now let me go a little bit more into some of our newer work where we're actually doing GI, but for much more a larger scale problem. So we haven't continued the work on partial specifications. I'm still very interested in it. We really need to explore that further, but I think it gives us a hint at some of the things that are happening. So I want to talk about a security issue that happened. So this has been called information leakage. So we have a program, and when we have a program, we have kind of two parts of data in our program. So we have that confidential data that we don't want anybody else to see, that shouldn't ever leave the program. And then we have public data, which is available to anybody that accesses the program. So suppose we have Sarah Hacker sitting there up on the right corner, and what she's going to do is she's going to have access to the public part of our program. And she can ask that program as many questions as she wants. She can send data to that program. She can try to create buffer overflows. She can cause a lot of problems. Now, what should happen is every time she sends a query to that program, all she should ever get back is the information in the public data. Unfortunately, occasionally, some of the data from the confidential part ends up leaking out. And this is something we call information leakage problem. And we do not want this to happen. So why do we care about this? Well, here's a real world example. This is OpenSSL, probably one of the most well-known examples. This was a library that was being used in across the board in Unix. And basically, they found that there was this information leakage, and we could actually, people could get private information. This was actually a memory issue, so they could access a buffer beyond where they were allowed to. And this was like a huge problem. It took 1.5 years for them to fix all of the systems that actually were using OpenSSL, because it was a library, everybody was using it. There's been other real world examples, such as the integer underflow in the Linux kernel. And all of these just sat on the system for a long time and then affected many systems. So this is a serious problem. Here's just an example of what happens in Heartbleed. There's this sort of structure, and there's this payload, and you can see it's all in C, and it's using memory types. And what happens is in the heartbeat, we basically send something to the victim, and then they return a message. And when we get this back, we actually, you notice here that the response sends back more information. So when we ask for the request, we add on some payload data, and it comes back, and we can get information beyond where we were supposed to see. And so it can leak information. Here's the patch. And so basically what they did, now this is a simple version of the patch. I've actually looked at the real version. It's a little more detailed. But basically what happens is if if we go over that payload, then we just return right away and end that. So in some ways, this, I argue, may actually change the functionality of the program, but we'll come back to that. So, but this is the patch that came out. So this is a memory problem. Okay, that's a very simple information leakage, but there's other kinds of programs that can also leak information. And I'll use our triangle example to give you some flavor. Now, this is, again, this is a simple example to explain it, but there are programs that work in a similar fashion that aren't just a triangle program. So there's a triangle guessing program. So here we have the same 3 inputs that we normally use in our triangle program. So we've got, and in here we've removed any checks for invalid triangles. So we're just going to assume that all of our triangles are good. And what happens is here, we have Sarah Hacker down here. She's asking questions. So if we look at the top, you can see we have 3 inputs, a secret input, and side 2 and side 3. So the user, the public puts in those 2 public inputs, and the secret is actually sitting in the program. It comes from somewhere else, and it's not supposed to leak out. So Sarah can put in public input 3 and 4. And if she does that and she gets an output scaling, well, you may jump to the assumption that it's neither 3 or 4. But actually, I don't know if you can do that because you don't really know the behavior of the program. Perhaps it's being obfuscated, perhaps it's not behaving as we think. So we get some information perhaps, but we don't get any real information. Now, suppose she puts in 5 or 6 and she gets isosceles. Well, now it's either 5 or 6, but again, we only get a little bit of information, right? We know that it's possibly that's the value, but we don't really know very well. So instead, what we can use is something called hypertesting. So in hypertesting, what we do is we run sets of tests and we look for changes. So if she was to run the first two, 10 and 7 twice, and she got scaling 2 times, we don't know anything about the program. But suppose she put in 10 and 7 twice, and 1 time she got scaling and 1 time she got isosceles. Now we have information. Now we can actually see that the program is indeed leaking. And in fact, based on what the value is of that confidential information, in this case, it happened to be different from 10 and 7. And here we now know it is either 10 or 7. So now we're getting real information. So this idea of hypertesting means that we need to have these sets of tests in order to get this leakage. Okay. So this all, of course, assumes we have a security policy which specifies how our confidential information is handled. And we have to have a property we're looking at. So this property happens to be that of what we call non-interference. And I'll just talk a little bit about that in a few minutes. But basically, we have to have a policy. So here we have this high secret is the information in memory is not available to the user. So this is for a program called ATalk. So we say what our low inputs are, what our low outputs are, and then we talk about our secrets. This is beyond the scope of what we're doing in GI, but we need to have this to solve the problem. Okay, so assuming that we have this, we can actually quantify how much information is leaking, and we can do this through using mutual information. And I thank David, who's in the audience, who's actually come up with all of, who's the person who's working with us on this. But basically we can say, okay, what is the amount of information that's been released basis the amount of information that's given? We can quantify information leakage. And if you can quantify it, you can now put this into some sort of fitness, and you can actually use this to do genetic improvement. Okay. So I'll tell you a little bit about journey down our path of genetic improvement. So people had been looking at this idea of reducing information leakage. Mostly they were using static techniques. These don't really scale. We always have, whenever everything's static, we have lots of false positives. Fuzzing can find some memory leaks, but even if either one of those finds the memory leaks, they still have to repair them. They can't fix them. And it turns out you'll see that often fuzzing can't find these memory leaks. And if you think about the triangle program, we don't have memory leaks. We have a different kind of information flow. So we know already that we're not going to have a technique to do it. There was some work prior to ours on automated program repair. This was on the Angelix tool, which basically fixed heartbleed. But what they did is they required a failing test case. So their technique would only have worked after somebody discovered the fault, created a test case for it, and this we know is sitting in the wild for years. So this wouldn't really help in our environment. We don't always have a failing test case. So this is work I did with my student Ibrahim, with Dan Blackwell at UCL, David Clark, and Justina. And so our first attempt was something we called hyper GI. So what we tried to do is we said, okay, we're going to do GI. We're going to have a functional test suite and a leakage test suite. So we're going to keep those separate. And we're going to do some test generation, and we're going to detect the leaks. And then we're going to use fuzzers to create our functional test suites. We're going to use this binary search technique, which I don't have time to talk about, but I'm happy to chat later, to be able to find the leakage itself, because actually generating a test suite to uncover that leakage is a challenge in itself. And that's still how we do that best as an open problem. Then we would do a little bit of leak localization. And finally, we would repair this, and repair in the sense of genetic improvement, repair it. And we just used a fitness. At the top, you can see we took the QIF, which was that qualified information flow you saw, and the fail rate of the program, and we just took half and half, and we used that as a weighted fitness function. So it's not really multi-objective, it's just weighted fitness. And here are some, and we actually ran these. So first of all, just so that you're clear, we used 2 state-of-the-art fuzzers. And what we did is we ran them 5 times for 24 hours, 20 times for 2 hours, using some randomly generated input seeds. And we did this for 3 programs, the triangle one you've just seen, and then 2 programs that have actually been reported as information leakage faults in the literature. So these are from the CV. These are reports on security faults. They were also presented in other papers. So we used the versions from a paper, a static analysis paper. And the fuzzer found no faults. So the fuzzer could not even detect the leakage, not as well as, obviously it can't repair it. So here's just some of our initial results. So just, I didn't highlight this, but on the left side, it says initial QIF. And so these numbers, they're non-zero, meaning we have leakage. So anything that's non-zero, the higher means the higher leakage. So you can see our triangle program had 0.8, and this Apple Talk had the highest. Post-patch PDF, this is our median, so it was pretty good. But then if we jump over to the actual fitness at the end, remember we're trying to get a solution that has both 100% correctness and no leakage. And we only could find that in one of our subjects. So the other 2 subjects, we had a trade-off. We couldn't actually reach 0 at this point. And some of the challenges we realized is that, we had to really, we're generating tests, and some of these, we may not be able to cover them in a very systematic way. And so there could be issues with our tests. So we stepped back and we thought, well, what should we do about this? And so we kind of see this trade-off here. I know Zoom is covering it, but what that's showing is, the leakage versus the functional. So there's that trade-off there. So let's look at our triangle program again. So, well, what's the simplest thing we can do? Well, we know that equilateral is the least common part of our program. So if we just, we start this program, the original program, our leakage is 1 because we're normalizing this, and our fail rate is 0. So this is our original program. If we just come to this equilateral and we get rid of it, well, now everything's either isosceles or scaling. So we've lost some functionality in the program, but we've also reduced the leakage. So this would actually give us kind of a balance of leakage of 0.2, failed of 0.2. So we're kind of still have, neither's perfect, but we're kind of getting there. If instead we just remove everything and always return scaling, now our leakage goes down to 0 and our failed is 0.69. I would have to stop and have you think about this for a minute. So most people would say, well, this is functionally incorrect, but it really depends on your objective. If your objective is information leakage and security, maybe it's not that incorrect. So I'll just let you think a bit. Okay, so we also looked at some trade-off on some of our patches. So this is just some very lightweight looking to see what our patches looked like. And I just wanted to mention this. So we tried to say what was something semantically equivalent to what a developer patch. So we didn't have a developer patch for Triangle since we wrote it, so we'll ignore that. But you can see that in ATalk and Underflow, less than 80% were what we call semantically equivalent. So we had to change the program in some way to get a fix. And then we saw cases where we had good reduction, but no functionality loss. So ATalk, we found that no leakage, but functionality lost. So you can see that we're seeing a lot of trade-off here. And so what that did is that led us to think, well, of course, this is multi-objective. So if we go to a multi-objective optimization, we can clearly solve this problem and we're done. So this is more work with the same set of authors. So this was work that appeared last year called Keeping Secrets. And we tried to do the same thing, but in a multi-objective environment. We also tried to scale this. So the idea was we wanted to scale this to more real programs because we'd only used the very small 3 programs in the first one. We wanted to remove, we had done some human mapping of identifiers. We kind of cheated a little in some ways in that first iteration just to make it work. And we also wanted to evaluate functional test generation. And I'm going to not say anything about the results of the functional test generation when I show you the results, but I do want to say, I think this is a really interesting area. And I think where we went wrong is we were actually looking at, could we automatically generate faults, and could we do that using the code, using a tool? So we're using fuzzers, and we tried using different kinds of fuzzers. So we tried to do ones that would give us a really nice expected distribution, and we thought that would help us. And in fact, I think this is a case where we have to think about going back to semantics and reevaluate it that way and come up with manual tests and think about the specifications. But that's going to be beyond this talk. So, okay, so leak reducer, we start again with a security policy and our original program. And now we have two things. So we can generate our hypertests. We have our leak reduction algorithms. We generate our functional tests, and here we can use different kinds of automated test generation. We used fuzzers. We could use something like an Evo Suite, except this was all in C, but we can use a equivalent C generation tool, or we can even manually generate them, which I would like to actually try at this point. Then we did our genetic improvement, and now we wanted to have both a single and multi-objective. So we didn't want to have that fitness that just maps them to a single fitness. So what we did is we combined Piggy and JMetal for this. So we're using Piggy in this environment because Piggy can go across many different languages. So we did have to add things like localization and some other pieces to it to make it. We actually added other single objective algorithms as well, but it works really nicely in the sense that it lets us just plug in any language. And then we use JMetal so we could leverage all of the multi-objective algorithms that it has. So did a few things. I won't spend time here, but we had to figure out how to do dynamic leak localization. And basically what we just kind of did is we would use our tests for leak reduction, and we would systematically remove different lines and observe how it changed if it had any impact on our QIF, or it had no, and we used that to sort of decide which lines were most likely related to that QIF, right? We added some new mutation operators. In our original one, we just used the standard replace, delete, and change, and we added something to allow some sort of if statements or more generative that we didn't have before. So we came up with our original subjects, but then we added a few more. So we added another similar to triangle, something called classify, which we wrote. And it's similar to triangle, except we're just classifying, I think it's 10 integers. And so we have just a larger space of splitting out different if statements. And we expected that to be much more similar and give us similar results to triangle, which is why we used it. We used the Heartbleed module, and we used the whole, we didn't just pull out the part of Heartbleed, but we just took the whole file, and so we have about 1,000 lines of code there. And we use something called Big Num, which is also in the OpenSSL library. Now we ran fuzzers as well, and we did use the sanitizer, because if you turn on the sanitizer, it does look for information leakage. And so it found, so at least it would find faults in Heartbleed and Big Num, but the others, again, we couldn't even detect leakage. So we kind of had an interesting thing happen. So what happened is, when you're dealing in security, we wanted to send this to a conference, and we figured we better just check with the developers of OpenSSL. So Ibrahim sent them a nice email and said, hey, we found this in Big Num. We want to report it. Just can you let us know if it's okay? And we got back this response, basically, which says that correctness has context. And again, this fits into this whole story, because what it basically said is it said, well, come on, if you look at memcopy, you look at string copy, and all of these libraries, all of them have information leakage, and it's up to how the user of that library uses that function. So they said, you're probably right, but unless it's being used in some other function somewhere that's allowing information to leak out, it's fine. So again, this comes back, is it correct? Well, the actual module has information leakage, but it's up to the user. So, and if you think about it, we know that about string copy. So it's really a context or your perspective of what's correct here. So I want to keep coming back to that. So we moved on and we were able to use it. Okay, so we ran our genetic multi-objective algorithms, and we just looked at all of the kind of standard tools. So we looked at the generational distance, the inverse, and we looked at hypervolume, and we went across all our algorithms, and then we used a bunch of different, because we were in JMetal, we could look at MoSel and NSGSA 2 and 3 and the SPA2, so we could look at all these different algorithms. And you could see whatever is bold here gave us the best results. We also could look at the medium number of solutions on each Pareto front. And in the end, SPA2 kind of gave us overall came out on top the most number of times, but we didn't see any significant difference between many of them. So all of them had some benefits. So many of them gave us a good solution. So these are some Pareto fronts. This is from SPA2. And if we look at this, well, first of all, I just put up here a bunch of green dots, and those are all the single objective algorithms. So if we were to get a single solution from our original kind of algorithm, this is where they would be. And then the Pareto front is kind of, blue line is the Pareto front, and this red line is something we call a global Pareto front, where we kind of took all the Pareto fronts and merged them to try to get something. So you can see we're getting this nice multi-objective view. What we're not seeing, and you may notice this, is there's really nothing in this really low bottom space. So we're aiming to get something at 0, 0, but we're not really seeing too many things that are getting into that location. Heartbleed actually is probably our best here, and big num. And those are because of the probably the way they're structured. So let's look at a couple of examples. So if we look at, for instance, something that had leakage of 0 and fail rate of 0.44, this is what actually happened. So it basically took out all of the equilateral again. Okay, it's not working, but it should be over. So it basically took out, and it's returning either isosceles or scalene. This one we've seen before already. So basically this is returning isosceles when it should be returning equilateral. So basically it just removed the equilateral here. That's what this one's done. And if we look at what happened in Heartbleed, you can see we actually got a pretty good patch. So this is part of the Heartbleed. This is our patch. And if we look at a developer patch, you can see that we're pretty close. So we're at leakage of 0, functionality of 0.003. So we're pretty close. And basically somebody probably could look at our patch from Leak Reducer and then figure that out. So here's that kind of developer patch where they return 0. And we're doing the same thing, but we've got a couple other little issues here, so it's not quite perfect. So kind of show you these examples. Hopefully you're getting this idea that it's very hard to come to you not change a program if you want to get this non-functional property to behave. So there's been some work on this idea called approximate oracles. And so what they've done in this particular paper is they've taken the requirement for correctness of the oracle and they've relaxed it. And these are actually real valued systems. They were doing some energy, they were optimizing for energy. And basically they try to say, can we just relax the oracle, maybe not be as strict, and will we get better repairs and for genetic improvement? And the answer is yes. And it's because I think it's because it gives them more degrees of freedom. There's also been a bunch of work, and I'm just showing a few things on patch overfitting. And this one here is kind of interesting because it basically talks about overfitting in semantics-based programs. And it says, we performed the first study on overfitting in semantics-based program repair. We show that semantics-based APR can generate high-quality repairs, but can also produce patches that overfit. And I'm going to argue that maybe that's okay, because those semantics are important, and those semantics are basically telling us what the program should do, and we may have to overfit to actually fix some of these programs. So I'm going to let you think about that a bit more. And then, of course, there's more here on avoiding overfitting using formal methods. So people have been talking a lot. So I want to go back to this trade-off. We're doing GI, and we're trying to trade off between functional and non-functional properties. But I would argue if we don't satisfy, so we're always concerned about it being correct. That's always what I hear. We want to keep it correct and also get those non-functional properties. But if we don't satisfy a non-functional property, if we don't satisfy a security property, or we don't have good energy usage, or we're not having good performance, can we really say the program's correct? And the specifications should really include both. And so maybe we really have to have a trade-off. I would also say we know test cases are imperfect. They're not the best specifications. And correctness is really going to be dependent on context. So I'm going to come back to this triangle program I had in the beginning. and think about this a bit more. So first of all, here, where should we remove this? Should we have the delay in the program? Should we leave this function in there? It really depends on how this system is going to be used, on what the developer wants. And if you saw the triangle program I used in all of our examples for HyperGI, we never even checked for invalid triangles. So we built a program that we used correctness, but actually, and we were careful when we wrote our test suites to make sure that we stayed in that envelope, but really, we weren't even correct in how we specified that program, yet we did, and we specified it. So I don't know if this is correct. I don't know which one's the right answer. And I think we have to think about that in genetic improvement. So my kind of parting thoughts, correctness based only on functional tests is probably insufficient. Both functional and non-functional requirements are really needed for correctness. I think overfitting could be our friend. I mean, I really like the work on specialization. I think we maybe are too worried about overfitting, and maybe we need to leverage it a bit more, as long as we use it in a guided way and we know what we're doing. And I think where I really like to do some work, and I'm happy to chat with somebody here, and happy to join forces. I think we need to study the differences between specification-based and code-based testing. So I've spent my whole research career in testing, and I think about testing a lot, and there are clearly differences between auto-generated tests based on code, specification tests. We know that based on models, we have very different characteristics when we think about what our coverage is, what our model is we're using to coverage. And maybe we need to think more about those and really study those more. I know some of you have already done that in the GI community, but we should probably do more of that in when we think about GI. So that's all I want to say. I've talked a little bit about our partial specifications, information leakage, some of our forays into GI, and now I'm happy to take some questions.